So, hello everyone. My name is Samuel. I'm from the AI team of CloudWalk. This is our weekly paper club, and this week I'm presenting the paper Unsupervised Clickstream Clustering for User Behavior Analysis, which is basically a technique to group user behavior, to cluster user behavior. And so, they start the paper talking about the importance of understanding behavior, like in online systems. You can use that to uh, predict some behavior. You can use that to improve target ads and to understand more about the business per se. So they say here that the intuitive solution when people are trying to understand behavior is to do surveys, but surveys are very limited in the sense that uh, you need a lot of efforts to get to a lot of users, and then always there is uh, you have to choose between quality and quantity, and so that's a huge limitation. And another limitation is that in surveys, people tend to they have like a biased view of herself. So they sometimes may say that do something, but they actually do something else. So you always have this kind of bias that's intrinsic to surveys. And finally, uh, the the reason that I think like the most interesting they they say here is that when you do a survey, you kind of have to know what to expect by the answers. So you wouldn't be able to predict like unknown behavior. So you do a survey like kind of expecting something, but if you do that, you cannot capture like new behaviors or something that you weren't expecting. So that are the limitations of service that they mention here. And then they introduce the concept of click strings to sort of like try to use that to predict, to understand better behavior. So click strings are basically like sequence of timestamped events that happens inside an online service. And then they talk about what uh, service that uses like the it uses click strings. What you need to have to be like a good to better analyze behavior. And first, they said that it must scale and function well on large and noisy clickstream datasets. And clickstream datasets tend to be very large and very noisy. And the second that they mentioned here is the ability to capture unknown behavior. So the stuff that I mentioned earlier. So you shouldn't, it kind of needs to be an unsupervised system. So you shouldn't have a priori labels. And the last thing they mentioned is that the system should be well understandable. Like the labels that you create at the end should be understandable by humans. And they claim that they did all of that using the algorithm that they developed here in this paper. So at a high level, like they use similarity metrics between click strings to build similarity graphs that capture behavior patterns between users. So like the edges captures the similarity and the nodes represents the click strings of the users. And then they use the iterative feature pruning, which is removing the most important features, and then they iterate to create the similarity graph, like with the most important, removing the most important features. So they get at the end they get like a kind of a dendrogram where in the top you have the most general behavior, and as you go down, you have more granular behavior of the users in the system. And to do that here in this paper, they use two data sets. The first one is from Whispers, which is, I didn't know, but it's a popular anonymous social network. And the second one is from Gang Wang. I don't know how to pronounce it correctly, but it's kind of China's Facebook. And so they use these two data sets, and then they are evaluated using two benchmarks. First, they evaluate if the algorithm is well understandable, so if the labels created is understandable by humans, and then they evaluate the cluster quality of the algorithm comparing to other clusterization algorithms like k-means. And now talking a little bit more about the data sets. The first one is the anonymous social message called Whisper. They create these categories of events, so browsing, accounting, posting, chatting, notification, and then the events they listed here as event types. So we have browsing events, account events, and one thing that I think is interesting that they did is to create this category of if the event is initiated by the user or not. So you have, for example, here notification events that the user only receives notifications. So it's like a passive event. So you can use that to identify, for example, users that don't have inactive users, like they don't do much stuff inside your system. And yeah, basically the same thing here for the China's Facebook Gang Wang and category events, event types. I'll not go into much details of the data sets, just like to give an overview of what they are using. And now talking about the actual algorithm, which I think is the most interesting part of the paper. They say here that despite differences in personalities and habits, their behavior patterns within a given system cannot be entirely disparate. So despite us being very different human beings, our patterns inside an online system should match somehow. And like they will create a hierarchy where the most important, the most general behaviors are in the top and the most granular are in the bottom. To explain the algorithm, I will share another screen here because I make a kind of a presentation that I think would be useful to explain how the algorithm works. Oh, sorry. So, first, like they define first the click strings. So the click strings they didn't define only using events. They also consider the time between events. So, for example, you have this consider like user one. You have the first event, and then you have a time that happens before the next event. And here, like they did the same event, and then they discretize this time. So to not have like 1 second, 3 seconds, they kind of discretize the time between like 0 to 1 second, 1 second to 1 minute, 1 minute to 1 hour, 1 hour to 1 day, and more than 1 day. So we have like these strict labels that they represent events as well, and that defines like the click string. So you have these two, they got like 2 click strings for 2 users here, and then right now. So the next step of the algorithm is to get all the k-grams, which I choose like k equals 3 here, which are the subsequences from the clickstream events. So you get this first 3 here, then this 3 here, and those 3, and those 3, and you get that for both of clickstreams. Then you get the set of all possible k-grams, like from both of these clickstreams, you get the set here. And here, like I created so that they repeat these two k-grams here. So you have, instead of 8 different possible k-grams, you have 7 here. And then they count the normalized frequency of each k-gram within its subsequence. Here I just counted, not normalized stuff. So the first clickstream has this first 4 events here, and the second clickstream has this first event and these last 3 events here. Then they calculate the polar distance between the 2 arrays. So they use the polar distance because they realize that the vectors will be very sparse. So the polar distance measures the angles between the arrays, not the magnitude between them. So they thought it would be more useful. So they calculate the polar distance between these 2 arrays here. And that distance represents how connected the edges of the 2 click strings are. So if the value is very low, they are very close. the value is high, they are not that close apart. So you do this for all the users, all the clickstreams users, and got this similarity graph here. And that's like the first step of the process. You do it a lot of times because it's a recursive algorithm, but then doing that, you get to this first similarity graph. So I will go back to the paper here. A second. So once you have this similarity graph, you start the clusterization part. And then once you have this huge graph, you run this divisive hierarchical clustering, and then to get these first two clusters here. Then the idea is, now it's like, which for me is the most interesting part, it's to run the iterative feature pruning to remove the most important features. Once you remove them, you run the clusterization again, and then you get another two, or I don't know how many clusterization you got, and then you also do that, you do it again, and do it again, and every time you calculate the modularity between the modularity of the graph that you're obtaining, and once you stop doing that when the modularity of those graphs that you're generating passes a certain threshold. So that's the way they created to like address if the cluster quality is good or not, by calculating the modularity of the graph. And like how they decide which features are the most important ones. And they do that. I will just zoom in a little bit to contextualize. They do that comparing the distribution of the users inside the cluster that has that feature and outside the cluster. So if the feature is very important, you would expect a distribution with a long tail. So more users will have that feature. And if it's not that important outside the cluster, you don't expect like a thin tail. So, and then once you get these two distributions, you calculate the chi-square of them, and then you have this score here. And after doing that with all the features in the cluster, they plot kind of distributions of the chi-square and do kind of like an elbow method to select like the features that are before the elbow, they will be removed, they're the most important ones, and those features will kind of represent the entire cluster. These would be features that describe the entire cluster. So that's the way they do the feature pruning, comparing these two distributions, getting the chi-square, and then selecting the ones that have the biggest chi-square. And yeah, that's basically how the algorithm works. Here they say that they can infer the meaning of the clusters based on the selected features during the pruning phase. So this is the assumption that you're removing the most important ones, the ones that differentiate this cluster to the other ones. And like the rest of the paper, they just like describing the system that they created, talking about how the visualization that they created to represent this cluster. So they created this pretty nice kind of way of seeing the clusters. So you can imagine this sort of like a dendrogram seen up, looking up the dendrogram. So you have these clusters here. And one thing that is, I think it's worth mentioning is that they say that 80% of the clusters have less than 5 features that were selected 5 features to describe them, and 90% have less than 10. So this indicates that the prevalence user behavior can be characterized by a small number of key feature dimensions, which I think is very important to the cluster being understandable. And so the remaining of the paper is just like they evaluating the cluster labels. They first, to evaluate the cluster labels, they conduct a user study where a control group evaluates each cluster label, see if can telling what they interpreted for each label and see if those interpretations match. Apparently they match. So they produced well understandable labels. And they did some case studies here, which especially the first one I think is very interesting because they claim that they were able to predict the evolution from one cluster to another. So they claim that they were able to identify which users will become inactive based on which cluster they started. So they calculated the clusters through three different periods in time, and then looking at from which cluster the person moves between each period of time, they will be able to predict if they are going to be inactive or not. So the first one is kind of interesting. The second one is just evaluating hostile behaviors because like, this Whisper is a anonymous chat, so kind of has a lot of hostile behavior. And the third case study here is to identify fake accounts in Civil in Rain. And the final part here of the cluster is, I'm not going to much details of the case studies because I think it's very particular to the data sets. And the final part of the paper is evaluating the cluster quality. So it's a comparison that they made between their algorithm and k-means and device hierarchical clustering without feature pruning. And I was talking to Matheus earlier. I don't know. I'm not sure how they implemented k-means in this case here, but apparently their results, they tested in three different tasks. The first one is to identify fake accounts. The second one is to identify the inactive users, and the third one is to identify blocked users. So in the first two tasks, they were like a little bit better than k-means and hierarchical clustering. And the last one, to identify blocked users, they got basically the same precision. And yeah, that's it. That's the paper. One final comment here is about the implementation. They say that because you have to calculate the similarity graph, because you have to like calculate pairwise between all the nodes here, the complexity of the algorithm is really high, like n square here. And they gave a suggestion to have a more like feasible implementation, which is to get a sample of users and then calculate the distance instead of calculating all the between all the pairs, calculate only between the center of the cluster. So that the complexity goes to nk, which k is a small number, the number of the clusters. So yeah, that's it. That was the paper presentation. And if you guys want to discuss something about it.
Okay, Samuel, really cool paper. I think really interesting points. Does anyone have any questions or comments for Samuel about the paper? Well, I do have some. I think one thing, I don't know if it's because it's like a paper from 2016 or not, but I thought it was a bit funny, like when they define the distance metric, like they use the polar distance, right? Which is a term that I never heard about it, but when you look at the formula, it's kind of similar to the cosine similarity, right? So I think maybe if the paper was published, a bit later, the guys would just use this other term, right? Because it's exactly the same logic, right? Oh, their interest is not the total distance, right? It's more like the angle between is kind of similar in that regard. But yeah, I think another thing about the paper, yeah, I think is your point, right? How they did the k-mean clustering in this case, because I think, I think when you're finishing your review, like they said like that maybe you could start with k-means and then go to hierarchical clustering or something like that. I think that makes sense, right? Because like you said, the complexity of the algorithm is way lower. But then there's the point, right? Because they built on the kind of like graphs, right? But in graphs, if you have the adjacency matrix, it still have a huge matrix, right? So it still have that similar problem, right? So it's a bit how we can change a bit of the scope to get the values, right? Because I think how they model this is interesting because it's like they have the different types of events, but they also have, the timing between events, right? I think
Yeah.
that is interesting. Yeah, the only thing that I think is a bit weird about the paper is like when they do the comparisons with k-means, right? Because the comparison, how much cases we got with fake accounts or blocked users, etc., which is okay, but still it's clustering, right? So clustering, you don't have labels, like you're getting the results that you get from your data. So to me, it doesn't make sense if you have unlabeled data and then you want to extrapolate that to classification problem. To me, that it kind of defeats the purpose, right? So you have this data, so you train a model to do that. If you want to build assess quality, right? I think it makes more sense to assess clustering quality with metrics like silhouette or anything like to see like, oh, if this data point on this cluster really is more related to the data points of his cluster or cluster of another cluster, right? So like, oh, it is missing right to the cluster of X cluster or X2 cluster. So it's just a thing that I think to me it doesn't make much sense because it's okay, but it's okay as a metric, I think. But to me, it's a bit. I don't know. I think that clustering is one thing, unsupervised learning is one thing, supervised learning is another thing. Like if you want to do if you want to classify things based on your cluster, it's kind of like, I think it's much more understanding data, the real value or unsupervised learning. But anything else, I mean, the paper is really interesting. I think it has applications that we could think of, right, to build from it. I think and I think also I was also talking to you, right? To me, the most interesting thing is first how they built the problem, right? This graph approach is kind of different, but I think the feature pruning, right?
Yeah.
Because you get like all your main stuff, like, oh, the guy uses the app, he opens the app a lot, and then you have a cluster with that. And then when for each subcluster, instead of getting the same thing of app usage, which maybe if we didn't prune, you'd get like in this cluster of people that use the app open the app a lot, you may have like a cluster that the guys that really open the app a lot of times, and then the guys that kind of doesn't open as often as the other guys, which is like doesn't provide us with much information, right? It's more interesting if we ignore this. That's an important feature, and get like, oh, this guy actually he checks his messages, or the other wants to write messages. I don't know. I think this feature pruning idea, I think it's to me it's the most interesting part. I think because then at each level we get different variables that will be important to analyze and have like, oh, what is the difference between each group? I think that's really interesting.
No, yeah, by far from for me the most interesting part was the feature pruning. I spent this week thinking on how we can implement this in our case, like without all the similarity graph stuff and this huge computationally expensive part. But yeah, for me that's I didn't get to a conclusion of how can I use that in our case.
Yeah, yeah, I think yeah, and I think like it also depends on how we design the the data, right? Because I think like since they were able to test on k-means, it should work on k-means, right? Because you also have the type of problems that k-means is not possible, right? Because like if you have if your data, you can't put your data in a feature space, right? Because like if you can only have a type of data that you only have the metrics of the distances between the data points, right? But you can't represent them on feature space like strings, right? If you can't like the compute a distance between strings, I don't know, Levenstein, anything like that. But you kind of can't, or you can, but you be that very sparse vectors, right? And here I don't say, I'm not meaning to use like the deep learning embeddings or anything like that. It's more like classical machine learning, I guess. So like you would have like very sparse vectors, maybe with the count of the words of letters or something like that, that maybe would not be very good as an embedding to compute like k-means clustering. But then you could have Levenstein, and then you could have the distances between each type of string, right? And then you can apply hierarchical clustering. So I think it's interesting, these things, right? What is the limitations of each approach, right? Because it's not that hierarchical or k-means one is better than the other, right? Each one, I think, has its own merits and also its own limitations.
Yeah. Do you wanna mention something, Fabio?
Yeah, I was gonna comment two things. I think there's a trap and there's an opportunity. The opportunity is that can you go to page 6, please? The image.
Sure.
Right. So no, before that. Yeah. So you have those little sequences of events, right? The n-grams, and they use humans to evaluate those sequences of events and translate this into what the cluster means, right? What is the actual behavior translate into language? So today, I think this is a pure GPT task.
Yeah.
Mm-hmm.
Makes it easy. And I think that the trap is the similarity they use is very difficult to calculate because the formula is like cosine similarity, right? But what are the features? The features are the n-grams that they find in common between the two users. So you select all the events, you see the sequences, the n-grams that are formed by each of the sequences. So because you have many different events, like the number of possible n-grams that you can find is huge. So you can count them all. You would have a huge vector. So for each pair of users, the vector that they compare, the dimensions of this vector are the actual n-grams found in the sequences for those two users. So the cosine similarity doesn't operate like matrix versus matrix, and you can do everything in parallel. Like the dimensions of the vectors are different for each pair of users. So this is probably a nightmare to compute in large scale.
Yeah. So, and that's why I kind of didn't understand how would be the clusterization that they are proposing at the end, like the more implementable solution that they calculate the centroids of the clusters and then they calculate the distance between the centroids instead of doing all the pairwise stuff. Because how would I define the features that will be in the centroid? Because like that's for me what's the really sticking.
Yeah, you would probably need to find which are the n-grams that are important for that cluster, and then you compute that vector for each of the users that you're doing inference for. But anyway, like there's two complexities. There's the number of pairs of users, and you can reduce this by sampling the number of users. But there's also the complexity of calculating the similarity matrix itself.
Yeah, that's why I thought like if I can only like use the idea of feature pruning, but in another solution, like I think it would be, because for me the most interesting stuff about this paper is the feature pruning, like the idea of removing most important features and then clusterization again, sort of to get them. And these features, like they determine what those levels of cluster means. So that for me is the most important, interesting part of the paper. But I don't know. I don't think their implementation is feasible for us at least.